All right, I think we are live on Clouder. Welcome to Deep Test 2021, the third workshop on this interdisciplinary topic of testing deep learning-based systems and using deep learning to improve and enhance software testing. For the second time out of 3 editions now, the workshop is held virtually due to the COVID-19 outbreak. So we hope that you were all safe during these times. We are extremely happy to see you here today, even if in person in beautiful Madrid. So let me first start by thanking the people who made all of this possible. Part of the team is based in Switzerland, specifically those in the top row. Whereas we had new comers this edition. Following the feedback from last year, in which the attendees encouraged the more industrial participation in the workshop. So we involved people from IBM Research, such as Eitan, from industry, such as Guy, and there was also the precious contribution of Professor On Shehori and Tipilajan Saha. Thank the people who reviewed the papers. They made an incredible job. They gave very precious feedback to our authors. But what are we going to talk about today? So we're gonna have two keynotes, one in the morning and one in the afternoon. At the end of the workshop, we'll close with the panel. And what, of course, the main content is going to be the paper presentations. We're going to have 2 in the morning and 2 in the afternoon. So we have decided to stream both presentations consequently, like successfully. And we are going to have the Q&A session right after the end of the second presentation. And we'll try to make it like a bit more interactive. So feel free to prepare your questions and we'll ask them to the authors. So we received 9 submissions this year, out of which 4 were accepted. And here are the main topics of the papers that are going to be presented today. We're going to talk about adequacy criteria for DL-based systems and how to compute them efficiently. We're going to have papers about prediction models using deep learning for testing the input validity of web applications. We're going to have mutation testing tools presented, specifically focusing on faults at the data level. And finally, we are also going to discuss about a very hot topic in ML, which is like how do we detect the concept drift automatically. So just like a final suggestion, like nowadays, like Twitter has become, the de facto platform on which research is shared and commented. So feel free to interact with us also on Twitter. Here's the official hashtag. All right. So without further ado, now I'll stop the screen sharing. And I welcome our first keynote speaker, who is Dr. Amir Ronen. While trying to, introduce Amir to you, I mean, it's a bit difficult because he had a very adventurous life. He was like a successful academic, and then he went to industry, and since then it's leading like groundbreaking research in AI. Specifically, Amir is now the chief scientist at SparkBeyond, and his interest is like in the born of machine learning and algorithms. Thanks to his background, during his doctoral study and postdoctoral studies at Stanford University, in which he was mostly focusing on algorithms and game theory and anything that has like a deep mathematical background. That made him also receive several awards, including the Gödel Prize and the Best Paper Prize at the International Joint Conference in Artificial Intelligence and the Journal of Artificial Intelligence Research. So I welcome Dr. Amir, and please feel free to start.
Thank you. Can you hear me and see the screen? Okay?
Yes, loud and clear. Thank you.
Okay, great. So thank you very much for the invitation. I will speak about solving problems combining data science and web knowledge, actually web knowledge automatically mined from the web. I would like to stress that this talk is about technology, not about a methodology of doing so. Here in the papers, not exactly the topic of the workshop, but I think it can be, it's partially related. I think it can be very interesting to you. As said, I'm Amir Ronen. I'm the chief scientist of SparkBeyond. And so I'm a little bit sick. I will probably cough during the talk a little bit. I'll try to avoid it. So this is joint work with various people from SparkBeyond, and in particular, I would like to mention the contributions of Daniel Carmon, Elad Shaked, and Meir Maor. Let's start with some motivational background, and specifically, I would like to speak about how do we approach problem solving or problem analysis in data science and in like normal life. So when we have a problem, so I don't know, jet engines and they get corrupted, or I have people and they get sick, or and so on. So there is like the data science approach or the machine learning approach or statistical approach, if you will. And in a very high level, I could say that it follows the following pattern. I need to first to gather a lot of data. And in fact, I have very, very hard assumptions that I need to satisfy about this data. In particular, it needs to be stable over time, ideally taken from an IID, which is actually it's almost never the case. The population needs to be unbiased. So simplifying, I'll say that this means that the population that I'm going to see in production when I put the system in the field, or when I do something in order to change something in the future, it's going to be the same population that I as my training population, and everyone that did some data science or put some system in production or have dealt with domains that are related to people like healthcare knows that this is also very hard constraint. I won't talk about causality literature in this talk a lot, but I need to satisfy assumptions like no hidden confounders, broadly speaking, meaning that all the root cause, the variable that are the root causes of the phenomenon that I'm trying to learn, that I'm trying to explain, are in the data, okay? And I need to satisfy, finally, an assumption called no target leaks, broadly speaking, meaning that the information that I'm using during training is going to be available in production. For example, if I'm using future events in any sense, it's a target leak. When I go and make the prediction in the future, I won't have the future of the future, okay? So this is the no target leaks, and there are other assumptions. So it's quite heavy constraints on the data. But suppose I have such data, then I follow a statistical approach, right? So I need to find phenomena which is correlated with the target, okay? And once I do, I can act upon my finding. So there are many ways of doing that. Acting can be to take feature values that I can affect on and change them. So for example, if I come into the conclusion that I analyze some sickness and I come to the conclusion that blood test is a good predictor, I can say, okay, I want people to have more blood tests or more frequent blood tests or blood tests for everyone. So I'll be able to better predict the sickness on time. Okay, so or if I predicting the success of a movie and I find that the advertisement budget is a good affects the success of a movie, I say, okay, I want to pour more money into the marketing and so on. So this is changing feature values. And again, there are a lot of questions about the distinction between causation and correlations. Maybe we'll touch a little bit about it later. Another thing that I can often do is to act upon subpopulations. Like if I analyze, I don't know, switch pipes or pipes that get corrupted, and I see that old metal pipes get corrupted a lot, then I may decide to replace this whole segment, this whole subpopulation of pipes in advance. Okay, so in this way, I change the reality for good. So this is the data science approach, like summarized very deep, briefly. And I would like to note that this is very, very different than what we do as human beings when we approach problems in real life. Okay, so in real life, if I have a problem that I know agents get corrupted or pipes get corrupted and so on, or people get sick, I will start to think about the problem. I will start maybe to read about it. I will start to ask myself whether there are known root causes of the problem, and if there are there do they apply to my case? Do they make sense? Are there potential solutions and so on? And once I mature my thought a little bit, maybe I'll make some more thought experiments or real experiments and so on. So this is very, very different than the data science approach. So the main question that we ask here, the topic of this talk, is can we build a technology, again, a technology, that combines the two approaches, the data science approach and the everyday approach to problem solving, and in particular to problem analysis. Okay, that's the setup of this talk. So what we'll do here, I will suggest to take textual representation of features extracted from the data to be a bridge between data, which is actually it's something in numbers, right, or in some mathematical types. Okay, I will suggest textual representation of features as a bridge between data and knowledge, word knowledge, if you will. I will then suggest to use word knowledge mined from the web as a proxy of human understanding and word knowledge used by humans when we are trying to deal with problems. And then I will describe several efforts that we at SparkBeyond took in order to build technology that combines knowledge mined from the web into data science. Okay, that's going to be the scope of the talk. A few comments. First, let me stress that this is work in progress. I'm also going to say that usually I like to give, or this talk is mostly high level. Okay, I will not get deep into algorithms, mathematics, and so on. I'd also like to say that there is very little theory on this topic. Actually, I don't know any paper. If you know, you're welcome to enlighten me. And finally, because of the online setup and so on, I left sufficient time for questions. So let's do them at the end, please. Great. So before I dive into the actual topic, I would like to describe you a technology that we developed in SparkBeyond called the Discovery Platform. There are also some open source such open source products. I'm not sure at the same level, and also some competition. But in general, this is a general purpose automated research machine or data science machine, if you will. And it takes data, usually data with a target. So we're usually in a supervised setup. There is something specific that we would like to analyze. And it takes this data and automatically turns it into features, okay? Phenomena that is correlated with the target. Also models, insights, and so on. I will more focus on features in this talk. In order to do so, it actually goes over a huge hypothesis space, including many forms of external knowledge automatically linked into the main dataset. And I can speak for hours about the technology, but it's not the scope of this talk. But what is going to be important for us is that we're going to have a textual representation of the features. Also for segments and so on, I will not get into it. And as I said, once I have a textual representation, it can be a bridge between the data, which is usually just numbers and things like that, and knowledge that one may find on the web. Okay, so it's like a critical message of this talk, if you will. Let me give you a quick example. This is a very simple pipeline, but it's a pipeline of house prices, okay? And you have all sorts of data about house prices, like, okay, the target here is the price. We would like to predict the price of a house. We have things like the number of bedrooms, the square foot of living, the total area of the house, and so on and so forth. We have many things. We do a little bit of work in order to prepare the hypothesis space, and then we push this green button which says learn, okay? And as a result, we get a model, but this is not a focus on this talk. But what is important for us now is that we get a lot of features which are correlated with the target. This is a very simple, fairly simple pipeline. So many of the features are just raw variables, but you can also see here a phenomenon that says that, okay, if I take the price of houses which are near me, it's a good prediction. Okay, which makes a lot of sense, right? Okay, so I will call these features, and as you can see, they're essentially composition of functions applied on the main data, along with some predicate that gives you true or false, and actually at the end we omit this predicate usually. Okay, so this is very briefly about SparkBeyond. Let me give you two more high-level examples. This is from a quite old project for us, but here it says there's a feature that says that colorful gadgets tend to be cheaper. Okay, again, the target here was the price of a gadget, and it looks a little bit obscure, but once you see some examples, you can see that these type of gadgets are meant to specific type of customers. So what I would like to stress here that the system can spot phenomena which is well beyond some simple numerics. Here's another example from a different project. Here the goal was to predict the the amount of sales of shops for a certain kind in a certain geography. And the finding was that shops, or the feature said that shops near recreational parks tend to sell more, tend to be more successful. So what I would like to say here is about the feature representation. So originally the feature was an auto-generated code involving the shop's location and some external knowledge and some functions, compositions that extract this knowledge from the data. And again, it was automatically translated into text, which is the important thing for us. So now let's go back to our goal. So we were given such a data science machine, if you will, and now we want to ask whether we can utilize knowledge mined from the web to make better data science. And how can we do that? So by better data science, I can say, okay, I want better AUC when the system is in the field or during test time. But I can actually speak about things which are softer, but even more important for us when we do data science with customers, which means that we can have a quicker dialogue with the customer. We have a better data science process. What we do will trigger more actions, more useful actions, and so on, which is actually softer. It's harder to measure, but it's actually more important, I think. So let me say one note on actionability. And this is my own thesis. It's based on a lot of experience. You can decide whether you buy it or not. But I would say that almost always a phenomenon is actionable if and only if it's both real and interpretable. So it sounds a little bit ridiculous. So for real means for me that it will indeed hold in the future. Okay? And in particular, it means that it doesn't stem from some data collection artifact that we have so often. I mean, we did in data science in general. And the reality is not going to change in the future too much and so on and so forth. It's actually a quite heavy assumption, need a leap of faith, usually, if you do data science in practice. And the second bullet means that the phenomenon is interpretable. I can understand it, and I would like to think about a Kolmogorov complexity-like definition that I can express the phenomenon in a few words. Okay, that's for me something which is interpretable. Again, you can accept this thesis or not. Let me give you two examples. Suppose I found the following segment. I'm analyzing churn, and I found that women under 25 are more prone to churn, in my case. So I claim that this is actionable. So although that the gender is given, okay, I cannot change it always, okay? And the age is given, so I cannot affect these variables, but if I have such a finding, because I understand it, I can act upon it. I can try to find the reasons why they're churning. Maybe there's a better competitor for this segment or not. And then I can change the product. I may market things differently. I may come with an offer and so on and so forth. These are things which are not in the data. But because I understood the phenomenon, I can act upon it. Here's another example. Fluctuations in engine temperature cause degradation, say degradation of a jet engine. And again, this is something that I can act upon because I understand it. I may be able to stabilize the temperature and so on. And what I would like to stress here is that there are many mathematical ways to express fluctuations. I can speak about the standard deviation. I can speak about the standard deviation after some smoothing. I can speak about the kurtosis and so on and so forth. So there are many ways to express that, but if I want to take another engineer and explain her or him what's happening, I will say, okay, look, there are fluctuations in the agent temperature that cause degradation. Okay, so this brings us to the first step that we are doing in order to bridge between data and knowledge found on the web. And the goal here is to take features that may be complex, there may be a complex compositions of functions, and in fact, you can also, this is a workshop about deep learning, you can also think how to do it in a deep learning setup. I am actually not sure that this is going to be so easy. But in our case, we want to take features like the one I described and map them into simple intuitive statements. And what I would like to say is that first, these statements, it's not going to be a one-to-one mapping, okay? Because as I said, the mathematics of a composition of function can be complex. But actually, often, as we will see, we can simplify it enough. So the essence of the system, the essence of the feature will be described easily. So we look for something which is coarse-grained, and it describes the essence of the feature. And again, why we do that, it's reasonable to find textual evidence in the web, for example, for simple generic phenomenon. Okay, like, okay, the temperature is oscillating, and this is very bad for engines. Okay, this is something that I can hope to find on the web. It's also, I think, a good proxy to how people think. The actual mathematical manifestation of this phenomena on my specific data set is probably not something that I'm going to find represented on the web, okay? So this is why this trade-off is important. It's also very good for easing the cognitive complexity of the user. So I won't get deep into how we do it, but I would say that we utilize a three main phenomena. The first one is that often, in particular in the case of time series, we have complicated features, but they have good Pearson rank correlation with the simple representative features. So, like, again, we have like the canonical example of temperature fluctuations. So the feature may be complex composition of functions, like I smooth and then I take something. But if I take the data and look at the Pearson correlation with something simple like the standard deviation of temperature, I see a good correlation. So in this case, it's fair to say that the essence of the feature is that the temperature is oscillating. As I said, at least in our case, we have functions, compositions, and they have semantics. So I often can look, I can do it in an algorithmic way, but essentially I can look at an expression and say, okay, this feature actually says that the shop's location is near a train station, okay? Just because I know the semantics of the functions involved. And finally, I can sometimes take the population, I can find an optimal cutoff for a feature, and I can say, this is the population, and I can characterize it in a simpler means. So once I have this simplification, I can often find rules that turning the simple representative features into coarse-grained statements. So let me show you an example. I hope you can see it on your screens. This is from a true data set that can be found on Kaggle, and it is about jet engine degradations. And as you can see, the features are very complex. But using the method that I just described, you can see in the left-hand side that very highly correlated with simple phenomena. So for example, the first feature is actually means that there are many events from sensor 11 in the last 15 minutes. Sorry, I will touch. Which is, of course, cognitively something extremely easier to understand in the left-hand side. And this is something that I can look at the web and think whether, or try to find out whether it makes sense. We'll speak about how we do it in a minute. The second feature is, again, a composition of functions, but essentially it means that there are large fluctuations in sensor 21, and so on. This is the output of a system. It's not something that is, it's not a mock-up. It's the output of a real, of our engine in this case. Okay, so great. So we have now, for many features, not all of them, we can have corresponding simple statements in plain English that describe their essence. Great. Now, the next step that we are going to do now is to say, okay, we have a feature, and now we want to know whether we believe this feature or not. I mean, whether we this feature is correspond to something which is known, it makes sense, and if not, I have to go and explore whether this is an artifact of the data collection, whether it's something special to my own use case, and so on. So here's a simple example. I have feature like age affects patient chances of getting diabetes. So I can ask, okay, is this something which is known? Yes or no? And also, is this something which is causal? As if you remember the second slide, I told you that we look for things which are correlated with the target. And in fact, this is, in some sense, the only thing that we can look for. But often what is really important is to say whether this is something that actually causes the target. Because if it is, we can change it often or we can affect it, and it will make and it will improve the situation, okay? So is this causal? Is this actually a confounder? A confounder, very briefly, is something that is that cause both the feature, the variables that you are looking at, and the target. So for example, a famous example is that summer causes ice cream and causes people go to the beach more. And therefore, there is a correlation between eating ice cream and dying from drowning. And of course, eating ice cream would not cause you to drown. So it's quite a headache when we do data science, and we can ask on the web whether this is a confounder or not. And if we want to broaden our knowledge, can we find articles on this topic and so on? So how do we do it? Again, just very high level. As I said, we can take the feature and translate it into a statement, a simple English statement. Then we can take this statement and the target and translate it into a series of web search queries, okay? And we can take a search engine and we can look, and we can ask a few queries in order to find candidate pages that may prove, so to speak, the assertion that the feature indeed causes the target, okay? So we do this, we get a bulk of web pages or web paragraphs, snippets from these web pages, if you will. And then we can do some NLP things like using NLI, if you know NLP, in order, we can take deep learning models that are designed for that, and we can ask whether these paragraphs, any of these paragraphs, indeed proves, as much as you can prove using text, proves the statement that in our case is that age affects the patient chances of getting diabetes. Okay? Here's a quick example. Again, I hope that you can see the screen. So it's from a churn prediction case. Here it's a fairly complicated data set. You have the main data set, and you have census data set, calls data set, schools data set, and so on linked to it. And the features themselves are very scary, but as I said, quite scary. You can often translate them into statements. So for example, the second, and again, the UX in all this talk are very exploratory. It's for research, so it's temporary. But here is just an Excel, so we don't have all the information here. But let's look at the second feature, for instance. So the statement is that data usage influences churn. And now the system applies the algorithm that I described, and it indeed finds evidence for that. Since it's Excel, you can also see the first evidence, okay? But here is the URL, and here is the section, the snippet from this URL. And indeed, it's eye-opening. It tells you that in this study, this is a churn study, and the main factors were age, salary, which is actually not in this data set, and data usage, and those who use data services more actually churned more. Okay? And for other features, by the way, this is a bug, it's not one anymore, but for other features which are indeed very specific and I think not generalized well, we didn't find evidence. So the thesis here, and again, you can believe it or not, is that features with evidence are less sensitive to data collection intricacies, so they will transfer better into the future, into different geographies, into population, which is a little bit different, and so on, okay? Because they correspond to phenomena which is more known. So why this is a very challenging thing to do? I describe you one algorithm or in a high level, but know that the problem of taking a feature and finding evidence for it is an extremely hard one. So all the examples here are from real projects. So here is the first reason. Many cases are even hard for humans. For example, we have in one case, the same case that I described earlier, actually, that stores located in areas where one can find laundromats sell more. And the question is, why is that? It was actually for convenience stores. And we actually conjecture that the reason is actually that it's not the laundromat themselves, but the fact that in such areas there are more foot traffic, there are more potential customers, there are areas of a certain kind. So the laundromat here is not the root cause, and it's very hard to explain, to understand such a feature, even for an expert. I will skip number 2. I think we're getting a little bit short on time. Here's another reason. In many cases, we have features, and they only hold, they correspond to some phenomena, but they hold only in the context of a very specific project. For example, we had a fraud detection project, and in this project, we found that accounts which are Hotmail, the email is a Hotmail account, are less prone to fraud. Now, why is that? So we conjecture that in this case, the reason was that these accounts were actually more veteran. They were there for more time, and we didn't have the email edge in the actual variables. So it was a proxy for that. No, it's not something which is universal. It was true only in the context of this specific project. So it's extremely hard to reason about that, again, even for humans. There's also an interesting technical open question that is very intriguing to me. Suppose for some of the features, we have some evidence, and for some of the features, we don't have an evidence. Again, the goal is always to be correct in the future, to generalize well. So intuitively, we trust features that have evidence more, and we would like to put a prior on them. But the question is, okay, but what is going to be the prior? I don't know. Also, it's not a very developed, I think, topic of how exactly to put, I mean, mathematically how to put prior on features, but I'm not highly knowledgeable here. But the main question for me is, what is the prior? I don't know. Okay, now let's go into something completely different. Now think that we are only starting a project, okay, or maybe even we're just scoping a data science project. And one critical thing that I would like to do when I do a data science project is to have all the relevant information in place, okay? So what I'm going to describe now is a service that takes a textual description of a target, like I'll show you examples in a minute, and then it will suggest what the service things should be the top drivers for this target. Now, how do we do it? The real secret sauce is actually to use GPT-3. We have the permission to do so. So we have a giant transformer that comes up with the ideas here, and then we should do some NLP in order to better the results and so on. But the real heroes here are OpenAI, okay? And it's funny, we're becoming like transformer psychology, if you will. You need to ask the questions right, and we have like an algorithm that translate the target description into a set of queries that we ask GPT. So here are a few examples. So in this case, we asked, what's the price of a house in Tel Aviv? Actually, it's somebody that tested the system that asked this question. And you can see that the first result is quite intuitive, but it's also something that a human being may answer, which is, okay, the distance from the sea should be important because Tel Aviv is like, it has a very nice beach. But I found the 10th, number 10 really inspiring, okay? The distance from a mosque. Now, maybe it's a coincidence. Maybe it just happens by coincidence. But if you know, I mean, if you live near mosque, it can be, you may have a lot of noise early in the morning. So it should definitely influence the price. And this is something that at least I wouldn't think about. So once I see this list of drivers, I can try to bring the enough geospatial information in advance to have this list of drivers covered. Let's see another example. This is from a project that we had. So here the target is damage to sewage pipe. And specifically, we allow in this service to focus also on properties of specific entities, for example, entities that we think should be important or entities that we simply have data on. So here we also ask the system to focus on the house and on the pipe. And okay, the house is kind of expected, like the number of people living in the house and so on, which is, I think, important for this project. But the answer of the pipe is very interesting, very inspiring, because we have things like the diameter or the age of the pipe or the material, which is quite expected. But we have also the number of bends in the pipe, which is really brilliant. It's not something that I may think about. And once I see this kind of list, I can think whether I can approximate this, even if I don't have the data, maybe if I can find a proxy of it, and so on. Great. Here's another technology, again, on the same line of connecting web knowledge and data science. So now we have a textual representation both for the drivers. Okay, I can either add them manually or use the technology that I just described, which is based on transformers. And now we can ask, so we have the features and we have the main drivers of the target. And I can ask, okay, here's a project, which drivers are not covered by any feature? This is very important because if I say, okay, I have an idea of how to get this driver covered, I may have a better AUC. I may have a better machine learning results. Okay, I may have lower error and so on. So the way we do it, semantic model. Here we use Google's universal sentence encoder. We can also use, we actually currently use a mix of that and SBERT, if you know some transformers. And you can see that the semantic model is not perfect. But you can see here that drivers like size, the age of the house, and so on are covered, but things which are related to the demand, to whether there is a public transportation in this area and so on, are not covered. And again, if I can surface these drivers and even and cause the data scientist to say, aha, I can find another source of information, either in the customer's data, either I will speak with the customer and find more data of the customer, or I can bring public data on that. It depends on the types of the project. This can greatly improve the overall result of a project. Okay, so let me wrap up. What did we do here? We offered using knowledge mined from the web and actually also from indirectly from the parameters of giant transformers, if you will, and integrate it into a data science system. And in order to build this integration, we offered or we claimed that having textual representation of features, this is the bridge. This is what facilitates this linkage. And then we spoke about 4 concrete technologies that we developed. The first one is how to turn features into coarse-grained statements. And again, it's less clear how to do it in deep learning, using deep learning. In deep learning systems, for certain types of data, I think it may be possible, although specific areas in, anyway, we can take it offline. And once we have the coarse-grained statements, we spoke about 3 tools. The first one is to suggest drivers for the target, and we use the GPT-3 for that. We spoke about coverage analysis of drivers by features using a semantic model. And I describe in high level an algorithm that takes features or feature statements and bring evidence from the web on them, including some causality, evidence for their causalityness, so to speak. And by this, I finished my talk, and you can ask questions.
Thank you, Amir. Very, very nice talk. I personally appreciate it a lot. Um, so it's really nice to see how things are done outside academia and in a real industrial setting. Because I mean, most of us academics are really now, focusing on deep learning techniques to learn features automatically to solve the representation
Yes.
learning problem, right? Whereas, I
Right.
mean, you're just like stating the opposite that for some random data, I mean, you are not actually using deep learning, but you're like describing them textually. So, but isn't it hard to have a textual representation for certain kind of data, such as like audio or images? Because
So
the as long as the input can be described textually and it is sufficiently semi-structured, then this sort of works. But for some kind of data, I think that's extremely hard, right?
yes, so whatever is opaque. Again, even for pictures, you often have models that extract objects. Like this picture includes, I don't know, scary. Uh, includes something that is, I don't know, a gun or something like that, right? So again, I'm just trying to look at the chat in parallel to answer.
Yeah, we have questions about
Uh,
the apps all over the place, especially
yes,
about the quality of the features that you extract. How do you know they are good?
right. So so I'll just ask. I'll just answer. In pictures in general, or in deep learning in general, the short answer is that I don't know how to do it. Again, there are efforts to explain parts of deep learning networks. I have mixed feelings about this literature. So the short answer is that I don't know. Okay. Also, in deep learning, there is nothing that forces parts of the system to correspond to any human concept. So unless you force such a regulation, such a regularization.
Mm-hmm.
So I don't know, but again, for specific problems, you can say, okay, what are the actual objects in this picture, and then you can come up with, and then you can do have textual representation, and then you can start to ask whether this makes sense or not. This can be an interesting exercise. Is this answer your question?
Yes. Can I add something on top of this feature like questions? Whether the textual representation can actually help to better discriminate the bias in the data.
Can the textual representation can what? Actually, it's easier for me to read the question. Can the
Mm-hmm.
textual representation can do what?
Is it more
I just
helpful
need to.
than any raw feature in detecting the bias that is inherently in the data? There is a
The
huge chunk of
textual
work saying,
representation.
in fairness in AI.
Yes. So of course, when you have a deep learning system is essentially opaque. So of course, it makes it much harder to reason about it. And of course, if you have a good representation of a system, you can also detect biases. I want to put the fairness and so on in aside because I'm very ambivalent about this literature, even philosophically. But I want, and also it's a touchy issue. So let's put it aside. But of course, a representation that you can understand can help you. Of course, if the system is immensely complicated, you probably cannot have everything in a way that you can understand, right? Because it will mean that the system is too simple in some sense, right?
Vincenzo, the great question, I think, because like we are scattered all over the planet, and yes, like whether different languages can lead to totally different, knowledge base for the models.
Okay, I think it's a little bit off topic. I mean, it's an interesting question, of course, and I don't know the answer. I'm not a language expert. Okay. I mean, you can deduct a lot about the. I need to tell you an anecdote. Okay, yesterday night I took the service of that I just described, and I asked it, what drives a human being happiness? And then I also asked to focus on some entities, and the wife was one of them. Okay. So the answer was that wife should be beautiful. And I have like a personal reason because my wife just finishes a job and then making a change in life and so on. So I got answers that, of course, have a huge cultural bias. Like wife needs to be beautiful, wife needs to be good with the kids, one wife needs to be obedient, and so on and so forth. So of course you have many biases, and biases are going to be different across languages, and different languages have also more different presence in the web. So of course, in general, the answer is affirmative. Let me just refer to, because we have like 2 minutes, on ask how can I check the quality of the textual features that we generate? It's an excellent question. I don't have a very good answer for it now, except the fact that we do use feedback of data scientists in order to check it. It's not a perfect, and again, the representation is a little bit lossy to begin with, okay? We know that it's lossy. So except for having feedback from actual data science, at the moment I don't have a good answer. Let me maybe take one last question. Bias, discrimination in the data, yes. I mean, it depends on the use case.
We add that already, I think.
Yes, great. Do you use some numeric threshold for statements like being located near something? Yes, internally, we again, if the features are selected, then it means that including the cutoffs that is automatically generated to be the optimal cutoff for the feature have enough information gain, also given the other features. So essentially the answer is affirmative, and we also have like some thresholding. Okay, how do you measure the confidence of your model predictions? Confidence of model predictions given train validation and test is a standard issue,
I see.
so we're no different than that. Okay,
All
there are
right.
standard techniques of doing
All
that.
right. Let's thank the
Different.
speaker. Sorry, I have to cut you out because